Hello everyone, I am B. Muhammad Arfin from 3rd year Aeronautical B section and I am here to present my topic ultrasonic testing. This ultrasonic testing is a testing upon the NDT method, which is non-destructive method. The testing methods are, there are two types of testing method that are destructive testing or non-destructive testing. In destructive testing, after testing, the material loses its functionality. Examples like chemical analysis, mechanical properties, etc. In non-destructive testing, the soundness of the material is tested without affecting its functionality, which means testing of a material without making any uh, instability to the material. NDT method enhances the reliability of the components or product at manufacturing stage or in service. Definition of NDT: the use of non-invasive technique to determine the integrity of a material, component or structure, or quantitative measure some characteristics of the object. Inspect or measure without doing any harm is an NDT, which is non-destructive testing. The NDT consists of various methods. First one is visual inspection, inspecting a material through our eyes. Second one is liquid penetration, which is PT. And third one, magnetic particle testing, MT. And eddy current testing, ET. And radiographic testing, RT. And our topic, ultrasonic test, UT. The applications of NDT methods includes flaw detection and evaluation, leak detection, dimensional measurements, structure and microstructure characterization, examination of mechanical and physical properties, stress or strain and dynamic response measurements, material sorting and chemical composition determination. These are the applications, and there are NDT application at almost any stage in the production or life cycle of a component. First one, to assist in product development. It helps to develop a product and to screen or sort incoming materials and to monitor, improve or control manufacturing process. It will help the manufacturer company to improve their quality, to verify proper processing such as heat treating, to inspect for in-service damages. These are the application for the NDT, which is very useful. And liquid penetration inspection. Here, a liquid with high surface wetting characteristic is applied to the surface of the part and allow time to seep into surface breaking defects. And a developer liquid or powder is applied to pull the trapped penetrant out the defect and spread it on the surface where it can be seen. Here is the procedure by using the liquid penetration testing. Here the man using the liquid to test the particle, which is the alloy. Visual inspection is the final step in the process. The penetrate used is often loaded with a fluorescent dye and the inspection is done under UV light to increase test sensitivity. The excess liquid is removed from the surface of the part. These are some photos explaining about the liquid penetration inspection. And magnetic particle testing. The part is magnetized. Finally, milled iron particles coated with a dye pigment are then applied to the specimen. These particles are attracted to the magnetic flux linkage fields and will cluster to form an indication directly over the discontinuity. This indication can be visually detected under proper lighting condition. This is the magnetic particle testing. Here, the North Pole and South Pole interchange when the crack is taken place in the object. The wave which can restrict their flow. Magnetic particles takes place there. The magnetic field got distracted in the cracked area. So we can easily identify which area the object can be corrupted. And the application of NDT methods. Eddy current testing is particularly well suited for the detection surface crack, but can also be used to make electrical conductivity and coating thickness measurements. Here a small surface probe is scanned over the pore surface in an attempt to detect a crack. Here's the man check by using the eddy current testing. By moving the probe in the object in the monitor, it can be monitored. The corrosion area can be monitored using the eddy current testing easily. These are the ultrasonic testing. The types of sound, it will create a high frequency rates. In frequency range 0 to 20 Hz, it is a infrasound and example like earthquake. In between 20 and 20,000, audible sound, it's like speech or music. And more than 20,000, it's an ultrasonic bought quartz crystals. In the introduction, some frequencies above human audible range is called ultrasonic sound. The ultrasonic principle is based on the fact that solid material are good conductor of sound waves and reflect at interfaces, whereby the wave are not only reflected at the interfaces but also by internal flaws, material separation or inclusion, etc. A considerable amount of information about the part being examined can be collected, such as the presence of discontinuity, part or coating thickness, and acoustical properties can be often be correlated to certain properties of the material. Definition. It's first one, resolution. It is the ability to detect nearby small defects separately, and sensitivity, the ability to detect the smallest defect. And third one, attenuation. At a grain boundary, the wave is partially absorbed, partially scattered, and partially transmitted. So the sum of absorption and scattering is the attenuation of the wave. Fourth one, acoustic impedance. The resistance offered by the medium to keep propagation of sound wave through it. Harsh. At times when the material is very coarse, the waves are reflected from the grain boundaries and we get small echoes which are known as hashes or noise. Basic principle of sound. A sound. A sound is produced by vibrating body and travel in the form of a wave. Sound wave travel through material by vibrating the particles that make up the material. The pitch of the sound is determined by the frequency of the wave. Ultrasonic is a sound with a pitch too high to be detected by the human ear. This is the diagram of sound wave propagation. By using a hammer hitting the object, the sound can be developed. The measurement of sound waves from crest to crest determine its wavelength by tau. The sound wavelength is inversely proportional to its frequency. Tau is equal to 1 by f. Several wave modes of vibration are used in ultrasonic inspection. The most common are longitudinal, shear, and Rayleigh surface wave. The velocity of the sound in a given material is constant and can only be altered by a change in the mode of energy. And longitudinal waves. If the particles oscillate in the direction parallel to the propagation of wave, then it is said to be longitudinal wave. The properties of longitudinal wave. It propagates by compression and rarefaction of the particle in the direction of travel. Can propagate in solid and liquid and also gases. It has the highest velocity and longest wavelength among all types of waves. It has lesser attenuation than shear waves. It is a sound propagation by the longitudinal wave. The direction of oscillation vary due to the different sounds. And transverse waves. If the particle oscillate in the direction perpendicular to the propagation of wave, then it said to be transverse or shear wave. Properties of transverse wave. Propagates by lateral shear at right angle to the direction of wave travel. Can only travel in solid mediums. And ultrasound generation. Ultrasound is generated with a transducer. A transducer, which is worked by a piezoelectric element in a transducer, converts electrical energy into mechanical vibrations, which is sound, and vice versa. The transducer is capable of both transmitting and receiving sound energy. In the transducer, they use a case, epoxy coating, backlink material, which is in red color, electrodes, which is outer of the transducer, piezoelectric element, which is in blue color, wear plate will be in downside, and ground wire, signal wire, and coaxial cable connector. The transducer is capable of both transmitting and receiving sound energy. Principles of ultrasonic inspection. Ultrasonic waves are introduced into a material where they travel in a straight line and at a constant speed until they encounter a surface. The probe has a piezoelectric crystal in it which is excited by extremely short electrical discharge, causing it to vibrate and produce ultrasonic waves. The probe is coupled to the surface of the test object with a liquid or coupling paste so that the sound waves from the probe are able to be transmitted into the test object. The operator then scans the test object. He moves the probe evenly to and fro across the surface. In doing this, he observes the instrument display for any signals caused by reflection from interval discontinuity. At surface interfaces, some of the wave energy is reflected and some is transmitted. The amount of reflected or transmitted energy can be detected and provides information about the size of the reflector. The time travel of the sound can be measured and this provides information on the distance that the sound has traveled. Behavior at an interface. The reflection takes place at an interface due to difference in acoustic impedance of the two mediums. In medium 1, the wave which is incoming. At medium 2, the wave can be transmitted. It is a reflected wave. Sound reflection at a flaw. When a probe is attached to the object, the sound which is travel through the probe to the object, which can be say as sound travel path, and the flaw in between them workpiece. Flaw distance. Not only the back surface reflects the sound wave, the same is done by every change in the composition of the material. A flaw too reflects the sound wave. Depending on the size of flaw, the back wall echo amplitude changes. By using the probe in the object, the corrosion should be known by passing the sound. Change in depth of flaw changes the position of defect echo on screen. When the flaw is near the probe, the defect echo is near the initial pulse. As the flaw changes its position, its defect echo also moves accordingly. However, the defect echo would always lie towards the left of the back wall echo. Wall distance example. In monitor, this can be visible. And flaw sizes. As the size of the flaw increases, the amplitude of the defect echo also increases. And if the amplitude of the defect echo increases, the amplitude of the back wall echo will decrease. If the flaw is capable of reflecting the whole sound wave, then in such a case there would be a no back wall echo. This is the flaw size examples. In few of them they can be vary through the corrosion details. There could be some testing techniques. They are the ultrasonic testing is a very versatile inspection method, and inspection can be accomplished in a number of different ways. Ultrasonic inspection techniques are commonly divided into three primary classifications. First one is pulse echo and through transmission. It is relates to where reflected or transmitted energy is used. And second one, normal beam and angle beam. It relates to the angle that the sound energy enters the test article. Third one, contact and immersion, relates to the method of coupling the transducer to the test article. This is the types. Pulse echo technique is the first one, and immersion testing. It's used in a wider area. In through transmission, it can be passed through the object. In pulse echo technique, the echo will be stay in the upper area, but in the through transmission it passes through the object. Pulse echo technique. In pulse echo technique, a transducer sends out a pulse of energy and the same distance for reflect energy, which is an echo. Reflection occurs due to the presence of discontinuity on the surface of the test article. The amount of reflected sound energy is displayed versus time, which provides the inspector information about the size and the location of features that reflect the sound. In here, there is a plate which is lower to the probe. The IP refers to the initial pulse, and F refers to the flaw, and BE refers to the black wall echo. When the probe is placed on the plate, the initial pulse will be higher. Due to the flaw, it will be lower. So here we can identify the flaw in the plate. Digital display showing signal generated from the sound reflecting from back surface, and digital display showing the presence of a reflector midway through material with a lower amplitude back surface reflector. The pulse echo technique allows testing when access to only one side of the material is possible, and it allows the location of reflector to be precisely determined. And second type, through transmission. In through transmission, a digital display showing received sound through material thickness. In digital display showing loss of received signal due to presence of a discontinuity in the sound field. These are some examples of through transmissions. A man which can place the testing material in both sides of the object. In monitor that can be analyzed. And final one, normal and angle beam. In normal beam testing, The sound beam is introduced into the test article at 90 degrees to the surface. In angle beam testing, the sound beam is introduced into the test article at some angle other than 90. The choice between normal and angle beam inspection usually depends on the orientation of the defect. The sound should be directed to produce the largest deflection from the feature. It is a normal angle beam which placed upper side of the plate. The sound path will carry the sound wave through the plate and the defect can be identified. And transducers. Transducers are manufactured in variety of forms, shapes and sizes for varying applications. Transducers are categorized in a number of ways which include contact or immersion, single or dual element, normal or angle beam. In selecting a transducer for a given application, it is important to choose the desired frequency, bandwidth, size, and in some cases focusing which optimizes the inspection capabilities. Probes whose beams are normal to the surface are called straight beam probes. Normal probes transmit and receive the sound waves normal to the surface of the test object. Probes whose beams enter at the angle are called angle beam probes. Angle probes transmit and receive the sound wave at an angle of the surface to the test object. And the equipment which are used in the ultrasonic testing. Flaw detector. The flaw detector are instrument designed primarily for the inspection of components for defects. However, the signal can be evaluated to obtain other information such as material thickness values. Both analog and digital display are worked here. Offer the user option of getting horizontal sweep and amplitude threshold. These are the machines. Data presentation. Information from ultrasonic testing can be presented mainly in three most formats: A scan, B scan and C scan. In data presentation, a B scan can be presented in a display profile view cross-sectional of the test specimen. Only a reflected depth in the cross-sectional and the linear dimension can be determined. A limitation to this display technique is that reflector may be masked by larger reflector near the surface. And C-scan. The C-scan presentation displayed a plane type view of the test specimen and discontinuity. C-scan presentation are produced with an automated data acquisition system such as in immersion scanning. Use of A-scan in conjunction with C-scan is necessary when depth determination is desired. This is the photo of composite components and C-scan image of internal features. And advantage of ultrasonic testing. It has sensitive to both surface and subsurface discontinuity. Depth of penetration for flaw detection or measurement is superior to other methods. Only single-sided access is needed when pulse echo technique is used. High accuracy in determination reflector position and estimating size and shape. Minimal part preparation required. Electronic equipment provides instantaneous results. Detailed images can be produced with automated systems. Has other uses such as thickness measurements in addition to flaw detection. There are limitations of ultrasonic testing. There are surface must be accessible to transmit ultrasonic sound. Skill and training is more extensive than with some other methods. Normally requires a coupling medium to promote transfer of sound energy into test specimen. Materials that are rough, irregular in shape, very small, exceptionally thin or not homogeneous or difficult to inspect. Cast iron and other coarse grained material are difficult to inspect due to low sound transmission and high signal noise. Linear defect oriented parallel to the sound beam may go undetected. Reference standards are required for both equipment calibration and characterization of flaws. And here we gonna seen about the ultrasonic testing full process and the equipments and the testing techniques. I hope you all understand this topic. Thank you.